All right, folks, we're back for another video. Listen to the calm, soothing voice of Mr. T here while you're doing your homework. Last time we did, histograms, whatever, not a little expected value. Wasn't terrible, but maybe not the most interesting. Today's is actually pretty powerful stuff, pretty interesting. So hopefully you get into it, and I hope you enjoy it. In class, hopefully, whoops, let's share my screen and let's do this properly. It's funny how you forget how to do all these things. All right, so hopefully we did this in class and our class little pop quiz, but if you were not here or you want a quick refresher, this is what we did in class. We took out a blank piece of paper and numbered your paper 1 to 10, wrote your name at the top. We didn't give you any questions. We just said, you got to guess the answer. There's multiple choice. It's A, B, C, D, E. You have 1 minute, okay? And then we switched and we graded, okay? Zoom people, isn't that funny? I first did this when we were in hybrid. So basically, it was a silly pop quiz in order for you to start getting this idea about what are the possibilities, right? So you have a 20% chance that you're going to hit each of these multiple choice and get them right? So what would be our expected value for this quiz, right? Our expected value for this quiz was that we would get 20%, right? 10 questions, we'd expect to get 2 of them right because we got a probability of getting 1 out of 5 right, 20%, okay? So this is going to start getting us to think about this really important idea that's called binomial settings or a binomial random variable, okay? Sorry, let me move myself again. Sometimes there's not a good spot for me. Maybe I won't let me make myself any smaller. Well, we'll just keep moving around. So in the pop quiz activity, you were performing what are called repeated trials of the same chance process. Certain conditions were met that formed what's called a binomial setting or a binomial random variable. Really powerful stuff, really useful. This is really cool stuff. Again, if I'm going too quick, you feel free to pause. That was just kind of intro, but feel free to pause and write this down if you want. You can use it on your next quiz. A binomial setting arises when we perform n independent trials. So they got to be independent, right? So in that multiple choice thing, what you picked for the multiple choice didn't affect the other ones that you guessed on, right? I mean, maybe in your own mind, you're like, oh, I picked an A, so maybe I'll pick a B. But in reality, they're independent. And then we counted the times that a particular outcome was a success. Okay, so we counted up how many did you get right on your quiz? Okay, there's a success and there's a failure, right? And we're counting successes. So those are the two main things for a binomial setting or a binomial random variable to occur. Perform n independent trials, and then we're counting to see a success. Okay, but there's other things, and there's 4 conditions, and you have to have these memorized or written down, hey, and you can use them on your quiz. But these are super important. We're going to be checking these settings and making sure that we are meeting these 4 conditions. So the first one is binary, okay? The possible outcomes of each trial can be classified as success or failure, right? You're either going to get a success or you're going to get a failure. There's no like, hey, we did okay. You know, it's like, yes or no. It's binary. You've heard about that before. It's a yes or no thing, right? Okay, super important in computer science, and because that's what computers do. It's either a 0 or 1. There's nothing else, right? Okay, so that's number 1, binary. Number 2 is independent. We already mentioned this one, right? Independent is knowing the result of one trial will not tell us anything about the result of any other trial, or one decision doesn't affect the other, and that's independent. We've talked about that a lot. Hopefully that's nothing new to you there. Number 3 is number. The number of trials n of the chance process must be fixed in advance. So you're going to have 10 questions on your test. We're going to roll this dice 5 times. We are going to shoot 100 free throws. It needs to be a specific number of trials before you start doing the probability. So one that wouldn't work is I'm going to shoot free throws until I get 10. That wouldn't work. That's not a binomial distribution, because, I mean, maybe it takes you 10 to get 10 free throws, or maybe it takes you 50. Okay, there's no set number, and that would fail the binomial setting. Okay, so that one could be a little tricky. You need a specific number of trials, and you need to know that before you start your probability stuff. And then lastly, we have same probability. Okay, there needs to be the same probability of success on each trial. Okay, so listen to the things I've been talking about. Rolling dice. It's always 1 6 1 6 1 6 1 6. Shooting free throws, you probably have the same ability to shoot a free throw each time, right? What else did we say? Getting multiple choice question right when you don't know the answer or the questions, you're just guessing, right? It's just random. They each have a 20% chance, okay? So what's something that wouldn't work? Well, probably like a free throw versus a three-pointer. That wouldn't work. Those are different probabilities, right? Golly, what else? It's stuff that's random, right? That all have the same chance of occurring. So when we did our spinners, think way back to our spinners, right? We were more likely to land on, what was it? 3? 3 had more of a chance of being land on. That wouldn't be a binomial situation, okay? Because that one had more probability of landing on it. Okay, so, or, you know, poker cards, like you have more chance of drawing a face card than something else, et cetera, et cetera. We can come up with other stuff. Those are those. They spell out bins. Do you see that? B-I-N-S. So you might hear me say this. You might hear the book say this. Check the bins. Okay, it spells out bins. Binary, independent number, same probability. Super important. These are actually really useful. Okay. All right. This thing will go away. Go away. There we go. Determine whether or not the given scenario describes a binomial setting. Genes children receive from their parents are independent from one child to another. Each child of a particular set of parents has a probability 0.25 of having type O blood. Sorry, it's type O. Suppose these children have 5 children of their own. Count the number with type O blood. So they each have the same probability, right? I guess we're saying type O is what we're counting, so that would be considered as a success. We have a certain number of trials, right? There's 5 children, and then they're independent of each other, right? So this should pass the old bins. Now here's a card one. Shuffle a standard deck of 52 playing cards. Turn over the first 10 cards one at a time. Record the number of aces you observe. Okay, this one would be okay. So shuffle the 52. Actually, it's not. Sorry, it's not. Catch me. Why is this one not okay? I was thinking of something else. What can happen here? It passes number of trials, right? It passes, that might be it. Well, it passes binary. A success is getting an ace. Okay, so it passes 2. But the ones it doesn't pass are independent and same probability, right? Because look what happens. Let's say your second card is an ace. Well, now your probability changes that your third one will be an ace because there's one less ace in the deck. So your probabilities are changing as you turn over these cards. Okay, and it depends if you get an ace or not. So this one would be no. This one doesn't pass the bins, is not binomial. This one passes the bins, is binomial. So the binomial random variable, the count of success is x in a binomial setting, and the possible values of x are obviously 0, 1, 2, 3, all the way to how many successes you could have, which is how many trials you have, right? You could get them all right, even if that's very unlikely, right? On that quiz, It's possible you could get a 10 if you were very lucky, right? It's definitely possible. Okay, so binomial probability formula. Suppose that X is a binomial random variable with n trials and probability P of successes on each trial. The probability of getting exactly K successes is the following. Let's write this out. This is a really nice little formula. And it is not too bad. Let me get my, sorry, I think I need to, yep, let's get a pen here. Go back down, we'll get some more space. Okay, so the probability formula for this is, we're using everything we just saying. So the probability that X is equal to a certain number. So let's say we were flipping 5 coins and we want to know what's the probability we get exactly 3 heads. Okay, what's the probability we get 3 heads, right? Here we go. This is how you do it. You do the combination. Aren't you excited we got combinations back? Of n trials and how many we want, K, times the probability to the K, right? The probability that you get a success, okay? So probability times, then we're going to do 1 minus the probability to the n minus K, okay? So I know there's a lot going on here, but it's really not bad, okay? And we will do this, right? And we'll go over this. So write this formula down in your notes so you have it. You can do it on a quiz. And let's go to an example and it'll make more sense. Okay. So let's go back to our genetics problem. Each child has a 25% chance of having O-type blood. There are 5 children. Find the probability that exactly 3 of the 5 children have type O. Okay, so we want to find the probability here that X is 3. Okay, exactly 3 have type O blood. Okay, we're going to set it up, use our formula. So we're going to do the combination. There's 5 kids. We want 3 of them. And then a success is 0.25 in this case because they want to have type O blood. So we're going to go to the 3rd, right? And then basically the second one is the opposite of what we just did, right? So what's our probability of not having type O blood? 75% chance. And how many people do we want to have that? We want 3 to have type O. We want 2 to have something else, okay? And then very simple, we're just going to plug this into the calculator, calculadora. And let's see. So remember how to do a combination. You go stat. No, you don't. You go math. You go probability. You pick number 3. And we did 5. Choose 3, which is 10. So it's going to be 10 times, and then 0.25 to the 3rd. Comes out pretty nasty. We don't have to maybe write that out. It's like, don't round it like I'm going to do it. Please don't. But it's something like this. Don't round it. You just multiply these all on your calculator. And then 0.75 to the 3rd. Sorry, I'm messing things up. To the 3rd? No, to the 2nd. To the 2nd, Mr. T. Okay, so we're going to multiply these all out. Okay, and so when you multiply these all out, we get 0.0879. Okay, so like 8.79% chance that exactly 3 of these kids with this setting, with these conditions, get type O blood, right? And again, we could find this for 2, 0, 1, 3, whatever. We just plug in this nice little formula and we use those binomial settings to find that probability. It's really kind of nice, right? It's using a little bit of everything we've done all year, which again is kind of cool. It's cool having a combination in here, right? So anyways, there we go on that. See what we got for our last one. We might do this. I don't know. We'll figure something out. Okay. So there you go. That's your info for today. Again, not a ton, but hopefully you took notes, you watched it, and there we go. Hope you all have a great day. Great to see you.